So I mainly will be talking about finite size scaling of the hierarchical 5-4 model in dimension greater or equal to 4. And I will usually discuss about the scaling limit and the plateau. And this talk is based on works with Gordon Slade and Emmanuel Mishta. The first paper here was uploaded on the arXiv last year, I think in July. And the second paper is in progress. I'd like to start my talk with the easing model that I guess many of you would be familiar with. I'm going to define the easing model on a general graph G with vertex set V and edge set E. And also, it has two parameters, beta and H. Beta is the inverse temperature and H is the external field. And then the probability of a specific configuration, sigma, is given proportional to exponential minus the beta times the Hamiltonian. And the Hamiltonian is the energy of the spin configuration. When two adjacent spins are aligned in the same direction, it contributes 0 energy to the Hamiltonian. And if they're in the opposite direction, it contributes energy 2. And also for the magnetic field, if a spin is aligned in the direction of the magnetic field, it contributes energy minus H. And if it's in the opposite direction, it contributes H. Then I will define the critical inverse temperature using the spontaneous magnetization. And beta C is defined as the infimum of all betas where the spontaneous magnetization is positive. So you can think of beta C as the following. When beta is larger than beta C, then you have a spontaneous magnetization of a magnet. And if beta is smaller than beta C, then the magnetization of the magnet vanishes. And it is known using low temperature and high temperature expansion that in dimension greater or equal to 2. So in this case, this graph should be replaced by d-dimensional lattice. And in that case, the critical inverse temperature is always a finite positive number. And statistical physicists are usually interested in the critical phenomenon, which means that we are interested in the behavior of the easing model when beta minus beta is sufficiently small. I'm not going to talk about easing model too much in this talk. However, it is believed that the phi-4 model and the easing model are in the same universality class, which means that they exhibit the same type of critical behavior. And also, I'll be talking about a correspondence between the easing model and the phi-4 model in later slides. Why you can expect that they are in the same universality class. So from now on, I'll be talking about the phi-4 model. I will define the phi-4 model on system lambda n, which is the d-dimensional discrete torus of set length L to the n. The notation here might be a bit confusing. L is a fixed number, and n is the parameter that decides the size of the system. And of course, because we're working on the torus, we'll be assuming periodic boundary condition. Then the lattice phi-4 model on lambda n is defined using two parameters, nu, which can be any real number, and g, a positive number. And the phi-4 model is defined using the Hamiltonian, which is a sum of a quadratic term and a phi-4 term with coefficient g. The quadratic term has the quadratic form minus Laplacian plus nu. Then the Gibbs measure, which is the probability measure of taking a specific spin configuration phi, is given proportional to exponential minus the Hamiltonian. And you see that this Hamiltonian is not multiplied by the inverse temperature as for the Ising model. That's because beta can be observed into the Hamiltonian. And also the spin configuration. I forgot to mention that the spin configuration can take value in n-dimensional Euclidean space. You can divide the Hamiltonian into two terms. The one is the minus Laplacian inner product, phi inner product phi term, and the other is the potential function term. So if you apply discrete integration by parts, then you can see that this phi minus Laplacian phi can be rewritten as gradient phi to the power of 2. So this should really be considered as a gradient interaction energy, which was also seen in the definition of the Ising model. And this Vn term is the potential energy of the sum of potential energy of each spin, and it is a sum of this quadratic term with coefficient nu and a quartic term with coefficient g. And if you consider a specific limit where g is set to minus nu and they tend to infinity, and then the exponential minus the potential function, when it is scaled appropriately, converges to delta 1 plus delta minus 1. So this makes a constraint for the spin to take only plus 1 or minus 1 value. So in this sense, we can say that the phi-4 model converges to the Ising model. The other direction is also true, and that the Ising model the phi-4 model can be obtained as a limit of the Ising model, which is a result due to Griffiths and Simon. So in this sense, phi-4 model and the Ising model can be obtained as a limit of each other. So you can expect what holds for the Ising model to hold for the phi-4 model and vice versa. And that's the primary reason why phi-4 model and the Ising model are in the same universality class. I'm also going to talk about the critical point for the phi-4 model. However, I'm going to define it slightly differently using susceptibilities. So in a finite volume lambda n, I'll define the susceptibility as a sum of correlation functions. So the correlation function is the expectation you see here. So it's the expectation of phi x inner product phi 0. And it is summed over all points x in the system lambda n. Then you can also consider the infinite volume susceptibility, which you can obtain simply by taking n to infinity for the finite volume susceptibility. And the critical point is defined as the infimum of all nus where the infinite volume susceptibility is finite. This definition is actually a bit problematic because for the cases where phi has only one or two components, then there's an inequality called the Griffiths inequality, and it implies that chi-n is a function monotone in both n and nu. So it is increasing in nu, n, and it is decreasing in nu. So chi infinite is always well-defined, and also nu c is always well-defined. You can think of a picture like this, where nu blows up near the critical value and decays to 0 when nu tends to infinity. However, for the cases where n is greater or equal to 3, this Griffiths inequality is not known, so the existence of the infinite volume susceptibility is not guaranteed in the first place. So we don't know whether the critical point is defined in the first place. So it's one of the points that makes studying the Pfeiffer model with multi-components very tedious and difficult. So I'm now going to present some known results about the Pfeiffer model. People are usually interested in the scaling limit and the correlation function when dimension is greater or equal to 4. The term scaling limit is a bit vague. I'll be coming back to this point later and also describe terminologies like ensemble scaling limit and macroscopic scaling limits later on. However, I'm going to present the results for now. So when you tune the value of nu to the critical value and set dimension greater or equal to 4, then it is known from the 80s that in dimension greater or equal to 5, that the scaling limit is trivial. So the scaling limits being trivial means that it is simply a Gaussian field. And it was later improved and extended to dimension 4 by Eisenman and Newman in their celebrated paper. And they proved that the macroscopic scaling limit, and when there is only one component in the Pfeiffer model, then the scaling limit is also trivial. I have also mentioned the result by Bauer, Schmidt, Bridges, and Slade because this result also plays a very important role in our paper. But to be honest, they are not really talking about the critical point scaling limit because they are considering a sequence of nus that converges to the critical value. And the type of scaling limit is also a bit different. They consider the ensemble scaling limits when the coupling constant G is sufficiently small. The other results are about the correlation function. It was first proved by Gawęcki and Kupiainen for the case where there is only one component in the spin, and later extended to the general case by Slade and Thornburg. That's when dimension is equal to 4 and G is sufficiently small, then the correlation function decays polynomially with exponent d minus 2. From what I said earlier, it might seem natural to expect that the same should hold for the Ising model. However, the story is a bit different. Proving the same is much more difficult for the Ising model. As far as I am aware of, the best known result about the decay of the correlation function for the Ising model is due to Sakai. And it says that when dimension is very, very large, then the correlation function decays polynomially with exponent d minus 2. And some of you might be wondering what happens in dimension 2 and 3. I've mentioned in the earlier slide that dimension 4 is the critical dimension, and something very, very different happens in dimensions below that. So it is expected that the scaling limit in dimension 2 and 3 should be explained using the conformal field theory, and the stories are very different. And as far as I know, they are still open problems. And also, people are usually interested in constructing the continuum limit of the Pfeiffer model rather than looking at large distance behavior or like probabilistic properties of this model. First, as I have promised, I will first explain to you what the scaling limits are. So people are there are different regimes of scaling limit. First, you can classify the scaling limit into UV limits and IR limits. The ultraviolet limits explains how a particular field theory converges to a continuum one when you consider a sequence of lattices with the mesh size going to 0. However, this is not the limit we're going to consider. We are going to think about the infrared limits, where we think about the macroscopic behavior of the field when the system size goes to infinity. So for example, we can think of a smooth function f on d-dimensional space, and then test the function phi against fn. So fn is the discretization of this smooth function. And for example, we can define fn inner product phi as sum of f x over L to the n phi x. And we can think about where this converges to, what type of distribution this has as n goes to infinity. And when you think about this, you should have this type of picture in mind. However, you shouldn't confuse yourself by thinking about this picture that the mesh size is going to 0. We are really looking in the opposite direction, where the diameter of the subpart of f is multiplied by ln, and it is tested against this function and this random field phi. Does anyone have any question about this slide?
No, it's very nice and clear so far. Thank you very much.
Thank you. And then there are also different types of infrared scaling limits. So there is first the ensemble scaling limit, which considers a smooth function f on d-dimensional torus. And then we will take a discretization fn, which is again given as f of L to the minus n times x. And we will test this function against this random field phi. And again, we're interested in what type of limit this has. And there is a different limit regime, a mesoscopic scaling limit. In this case, there's a smooth function f in d-dimensional space. And again, take the discretization fm and test this function phi against fm. So in here, I'm taking two different limits here because m is the mode of how you discretize this function f, and n is the size of the system. So n should be much, much larger than m in order to for this inner product to make sense. And also, depending on the rates, how they diverge to infinity, the limit itself can also change. And then there's also macroscopic scaling limits that I have written for the Eisenman and Duminel-Kopeng results. I'll be talking about that later. So the first scaling limit result is about when nu is strictly greater than nu c, and it is a result due to Bauer-Schmidt bridges and Slate. So they proved that when G is sufficiently small, there is some value nu c such that when nu is nu c plus epsilon with epsilon sufficiently small, then phi tested against fn with scaling factor L to the minus d over 2n converges to white noise with variance m to the minus 2. Here m is called the effective mass of this system, and the asymptotic as epsilon goes to 0 can also be computed. So I didn't write this in this slide, but you can also compute the susceptibility of this field using this formula. And you find out that the susceptibility is also given by m to the minus 2. So you see that the susceptibility diverges as epsilon tends to 0. And if you remember the definition of the critical point, it's the point where the susceptibility starts to diverge. So this statement checks the validity of nu c as the critical points. And it is proof for the ensemble scaling. However, it is not unreasonable to expect that this holds for any type of mesoscopic scaling limits. The next result is about ensemble scaling limit where nu is close to nu c. So in this second result, we are taking f to be a smooth function on 4-dimensional torus and also s to be a positive number, and consider nu equal to the critical number nu c from the previous slides plus s times L to the minus 2n times n to the gamma hat. So, and for this specific choice of nu, we see that this field, random field phi, when scaled with a different scaling factor L to the minus d plus 2 over 2n, converges to Gaussian free fields with mass alpha s. So alpha is some positive number, and this mass is given by this parameter as how close this nu is to the critical points. There are several remarks about this theorem. First of all, this limit doesn't make sense when s is put to 0. In other words, when nu is exactly equal to nu c. However, this limit can still make sense when this function f has average 0. However, this limit cannot be dealt with the method of BBS. And finally, I said that the scaling factor changes when we're near the critical points. However, from this statement, the origin of the scaling factor is not so clear. This origin of the scaling factor is perhaps better explained in the Eisenman-Dumino-Coppens theorem. So they look at exactly the critical points, and for the case where there is only one component for the phi formula. And in their statement, they test this function random field phi against this function fm, and it is scaled by sigma m, which is a square root of sigma m, where sigma m is the variance of the sum of field value phi x, where x are the points inside the box with side length L to the m. And here I have put quotation mark in limit where n goes to infinity. So they consider the limit where the size of the seam stem diverges much more faster than this number m, which is a parameter that indicates how you discretize the smooth function f. And under this limit, you see that it converges to Gaussian fields with covariance metric C. There are also a few remarks about this theorem. First of all, if you remember the list of known results, it is known due to Gawensky and Kupiainen that if G is sufficiently small, the correlation function decays polynomially with exponent 2. So 2 is equal to d minus 2. And therefore, if you just compute this, if you just insert this formula into sigma m, and then you see that it's asymptotic to L to the 2 plus d times m. So you see that 1 over square root sigma m is actually the same as the scaling factor of Bauer, Schmidt, Bridges, and Slade, and you see that that is where the scaling factor comes from. However, there is also a confusing point because they are looking exactly at this critical point and they are using the same scaling factor. However, they obtain a different scaling limit. So for the case of Bauer, Schmidt, and Bridges and Slade, the scaling limit was not defined when S is equal to 0. In other words, nu is exactly equal to nu c. However, for the Eisenman-Newman-Koppang, they obtained the Gaussian field as a scaling limit. And this is due to their use of the boundary condition. So they use the 0 boundary condition instead of the periodic boundary condition. One of our contributions in our paper was to clarify the role of this boundary condition when you study the critical phenomenon. And finally, the covariance matrix C here is not specified for Eisenman and Newman-Koppang. So to summarize, we looked at three scaling limits. The first result was for nu strictly greater than nu c, and in that case, for both ensemble and the mesoscopic scaling limits, white noise was obtained as a scaling limit. The second result was about ensemble scaling limit when you consider a sequence of news that converges to nu c, and Gaussian free field, a massive Gaussian free field was obtained. And the third result was due to Eisenman and Newman-Koppang, where they obtained as a macroscopic scaling limit a Gaussian field, and that was exactly at the critical point. And
Can
as
I
have
ask a clarification? Sorry.
Yes, sure.
Just on the previous slide. Yeah. So phi here. Am I thinking of phi as as a collection of sort of n or n to the d points, or am I thinking of phi as in RD?
Yes, their own lattice points.
Okay, so
Yeah.
it's lattice points, right? Okay, fine.
Yeah.
So does phi also have some dependence on n then?
Which n? Small n or large n?
A large n.
Does it have dependence? Or
yeah, because
what?
you're projecting onto the lattice, right? Or
Yes.
okay, so the size of phi is capital N, right? Or I'm just trying to get a hold of this inner product you've written in equation 12, this FM phi.
Oh yes, this one. Yeah.
Yeah, exactly. Okay, so remind the notation FM, can you just remind me what that means?
Oh yes, sure. So it was defined this mesoscopic scaling limit.
Right, okay.
So there are two parameters. N is the size of the system, and M is how you discretize this function f. So Fm is to the minus m times x.
Okay.
So helpful if you think about this picture. So if this blue region is the subpart of f, then you rescale everything so that so you rescale the lattice so that the L to the m times the diameter of the subpart of f is within this region, within this blue region. Do you see how
Yeah, I see what you mean. Yeah, sorry. So I think I was thinking more along the lines of equation 7, so this slide actually clarifies things a lot for me. Yeah. Okay, thanks very much.
Great. So as I've explained, there are few questions you can ask from these results. So for example, why are BBS and Eisenman-Lumina-Koppen results different? And also, what is the ensemble scaling limit at the critical point, and so on. And these questions were one of our main motivations for studying the finite size scaling. Our next motivation is due to the plateau effects in various different models. So to explain what is a plateau, I think it's better to explain what is not a plateau. For that, I will consider a massive Gaussian free field in dimension greater or equal to 3 with mass equal to L to the minus 2n times mn squared. So the mass square is equal to L to the minus 2m times mn squared. And when mn tends to 0, then the 2-point correlation function has two main contributions. One is the polynomially decaying part, and the other is the constant term. You can derive this asymptotic using the random walk representation of the lattice Green's function. And this constant part can be considered as a result of the recurrence of the random walk on a discrete torus. So here we are again considering a periodic boundary condition on d-dimensional torus. And also the value of the second term can be guessed using the susceptibility. So in this case, the susceptibility can be computed exactly as the inverse of the squared mass. So it is simply mn to the minus 2 times L to the 2n. And from this formula, you can observe that a flat region appears when this term dominates. So for example, if you plot the graph of the 2-point correlation function as a function of distance between x and y, then initially it decays polynomially, but when the distance gets larger and m to the minus 2 times L to the minus d minus 2n dominates, then you see a flat region appears. However, this is not the plateau. And there are two main reasons behind that. Firstly, the proportion of this flat region in lambda n does not converge to 1. And secondly, the value of this correlation function inside this flat region doesn't really converge to a single value. It's just that it's in a scale of m to the minus 2 times L to the minus d minus 2n. So to define what a plateau is, you can exactly think about the opposite, where the correlation function, when there's a flat region where whose proportion inside lambda n converges to 1, and the value inside the flat region converges to a single value, then you say that there's plateau inside the correlation function. So what I want to emphasize here is that plateau is more than just recurrence of a random walk. It is really a critical phenomenon, and there is more complex mechanism behind the plateau, more than the recurrence of the random walk. The first example, proper example for the plateau is due to Hutchcroft, Mishta, and Slade, and they have proved that for side percolation with d greater or equal to 11, the connection probability inside this side percolation at the critical point has two main contributions. Just in case, are you familiar with this side percolation? I mean, it doesn't really matter, but I was having probabilities in mind, but anyway, so It has two main contributions. One is a polynomially decaying term, and the other term is the constant term, which we can interpret as the plateau term. So if you plot a graph of this correlation function, it has two regions. When x minus y is sufficiently small than this number here, L to the 2d over 3d minus 2n, then it shows a polynomial decay. And when it is larger than this number, then it shows a constant behavior. So L to the minus 2 over 3d, and that's what the v, I didn't explain what v is. V is the size of the system. So it's L to the dn in our case. So for this case, it is showing a genuine plateau. The second example is due to Papathanatos. So he proved for the Ising model with dimension greater equal to 5 that when beta is attuned to the critical beta, then the two-point correlation function satisfies a lower bound that has two main terms. The first one is again the polynomial, the decaying term, and the second term is a constant term, which is again interpreted as the plateau. However, this lower bound is conditional on the infinite volume lower bound of the two-point correlation function. And that is the reason why I put the theorem inside the quotation mark, because in the original paper by Papathanatos in his graduation PhD thesis, he didn't realize that the condition on the lower bounds of the infinite volume two-point correlation function is required. So the proof was not complete. However, it is a very insightful paper, so I don't want to undermine his results. Anyway, as I have also and as I have said in the slides before, that for the case of the Ising model, this lower bounds, polynomial lower bound, is only known for sufficiently large dimensions. That is the result by Sakai. So we expect that the same should hold for the 5-4 model. So our goals are the following. We would like to first study the infinite volume scaling limits in dimension greater equal to 4, and also identify the plateau in dimensions. Oh, well, I've written here dimension equal to 4, but it should be greater equal to 4. And we would like to achieve these goals by developing a general framework that enables the study of lattice models within the same universality class. So our method was the renormalization group methods. I don't think many of you be familiar with this terminology, but it's it just means a multi-scale argument mainly used by physicists for studying statistical and quantum physics. However, recently, probabilists have also been importing their methodologies, and it has been proven quite fruitful in this context of lattice models. No, I will start presenting my results. But before that, I would have to define what the hierarchical models are, because our results are not on the genuine 5-4 model, but rather on the hierarchical model. So we first have to define the hierarchical metric. So the hierarchical distance between points x and y is defined as L to the jxy, where L is a fixed parameter, as we have defined before, And jxy is the smallest j such that x and y are in the same j block. So I think this picture would be helpful to understand what j blocks are. And in this picture, L is simply equal to 2. And the 0 blocks are simply just points, and 1 blocks are 2 by 2 blocks, 2 blocks are 4 by 4 blocks, and 3 blocks are 8 by 8 blocks. The important fact is that the hierarchical distance is asymptotic to the usual Euclidean distance when x minus y tends to infinity. So that's the reason why we expect the hierarchical model is not too different from the usual model. And also we consider the hierarchical random walk. So we define it using the probability matrix Pxy, and it's given by a constant, so a normalizing term times hierarchical distance to the minus d minus 2. And the minus of hierarchical Laplacian is defined as I minus P. So this H is a typo there. So at first sight, this definition of the hierarchical Laplacian may look very weird. However, if you think about the Green's function of this hierarchical Laplacian, it has the same rate of decay as the Green's function for the usual Laplacian. So you can expect that the hierarchical model also shows the same type of critical behaviors as the usual, the Pfeiffer model. And the hierarchical model is defined simply by replacing the minus Laplacian that was used to define the Pfeiffer model by minus hierarchical Laplacian. And everything else is the same. The Gibbs measure is the same. The susceptibility is the same. And also the infinite volume susceptibility is the same. The first set of results is about scaling limit. And the first theorem is proved in our first paper for case dimension greater or equal to 4, any n-component model and G sufficiently small. And it states that there exists a positive, negative critical number nu C, such that for any positive number epsilon, the infinite volume susceptibility at nu C plus epsilon is given by m epsilon minus 2, where m epsilon here is the effective mass, and also is asymptotic as epsilon going to 0 is given by this formula in equation 20. And you might notice that this theorem is very similar to the Bauer, Schmidt, Bridges, and Slade I showed you earlier, because it simply extends their results. However, it does significantly more, because for their case, they required epsilon to be sufficiently small. However, in our case, epsilon can be any positive number. And also, we also proved that chi infinite is a monotone function in nu. So we didn't state it in our paper. However, we could also obtain that when nu goes to infinity, that chi infinite decays polynomially. So we have a polynomial upper bound and the lower bound on the decay of chi infinite. And well, according to this formula, equation 22, we know how it diverges as nu tends to nu critical. So this nu C can be characterized by this equation 21 here. So it's infimum of all nu's where chi infinite of nu prime is finite for any nu prime greater than nu. So if you think about it, it's not exactly the same as the definition of the critical point I showed you earlier. But however, I think this is a reasonably good characterization of nu C. And it does a perfect job, I think. Well, equation, this nu C is not equal to the definition of the critical point because we don't know what happens below this nu C here. And then the highlights of our paper was on the non-Gaussian scaling at the critical point. So if you look at the critical point, then the sum of phi x's, when you scale it by L to the -3/dn for case d greater than 4, then its distribution converges to non-Gaussian distribution weighted by exponential minus x quartic term. So it's a non-Gaussian limit. And for the case where d is equal to 4, you only need an extra logarithmic correction term here, n to the -1/4. And therefore, you can also compute the finite volume susceptibilities and how it diverges at the critical points. Yes, at the critical points. We have also looked at the critical window. So the critical window is simply the range of news in a finite volume where the system shows a critical behavior. And for dimension greater than 4 is given by the size of the window is given by L to the -d/2n. And for dimension equal to 4, it is extra logarithmic correction. And within that window, when nu is equal to nu C plus SWN, then the same object converges to a non-Gaussian limit, but with extra factor is exponential CS times x squared. So to be honest, this is not really, not the scaling limit result, because we are only looking at the limit of the sum of phi x's. So we didn't call it a non-Gaussian scaling limit. I just said that it's a non-Gaussian scaling n limit. However, this is a strong indication that the scaling limit is also a non-Gaussian distribution. The reasoning is as the following. So if you remember, according to BBS results, the phi, the random field phi, if you rescale it by L to the -d of d plus 2/2n, then it converges to a massive Gaussian free field with mass alpha times s. And you can simply take s equal to 0 at the critical points, and then this function f should be such that its average is equal to 0. So inspired by this, we can decompose a general function into its average f bar plus f minus f bar. And because the average of this f minus f bar is equal to 0, you can put this inside this expression on the right-hand side here. However, because the scaling in our theorem, L to the 3/4dn is much, much larger than the scaling of BBS result, we see that under the scaling of our theorem, phi tested against f minus f bar converges to 0 as n goes to infinity. On the other hand, the average part, f bar here, if we test it against phi, then it's simply given by L to the -dn times sum of fx times sum of phi x. And we know how this sum of phi x converges. I mean, where does it converges to? So we see that the contribution of the mean of this function f dominates in the limit where n goes to infinity. Therefore, we can compute the scaling limit of a general field when its mean is not equal to 0. Our next result clarifies the the difference between the Bauer-Schmidt-Bridges and Slade result and Eisenman-Dumel-Köpping result. So we look at zero boundary condition case. And we see that when nu is equal to nu c minus a specific value we call Vn, then and the hierarchical phi-4 model actually shows exactly the same type of scaling. It's not a scaling limit, but it shows exactly the same type of behavior as we have seen for the periodic boundary condition and nu equal to nu c. And that shift of the critical points Vn is given proportional to L to the minus 2n when d is greater than 4, and with a logarithmic correction when d is equal to 4. So we see that well, Eisenman-Dumel-Köpping result was different from BBS result because when they were thinking about zero boundary condition, the effective critical point was actually shifted to the left by an amount Vn. So when they are looking at the critical point, they are actually away from the critical points by considering the zero boundary condition, and that gives one advantage. And also, I didn't mention this result in this slide. However, you can also reproduce the Eisenman-Dumel-Köpping result when nu is equal to nu c and with zero boundary condition. So to summarize, we have looked at critical points, both for dimension equal to 4 and greater than 4. And there was a critical window with width Wn. And for zero boundary condition case, the effective critical point was shifted by an amount Vn. Our next set of results are on Plateau, but because I don't have much time left now, I will go through this very quickly. Again, we have similar results for dimension equal to 4 and greater than 4. I think it's better to go to this slide first. So when x is sufficiently smaller than L to the d over 2d minus 2n, then the 2-point correlation function shows a polynomial decay, whereas in the other regime, the 2-point correlation shows a constant behavior. So it shows that this theorem shows that the hierarchical phi-4 model shows a genuine plateau in the sense that the region where you have a constant value converges to 1 as n goes to infinity. And also in this flat region, the correlation function really takes a constant value. I would like to conclude my talk with some conjectures and perspectives. So as I have mentioned, I would like to show the ensemble scaling limit exactly at the critical points of the phi-4 model. And also we expect that the same picture should hold for models in the same universality class, which includes the Euclidean or the usual phi-4 model, not the hierarchical one. And also Owen's lattice spin models, which includes the Ising model when n is equal to 1, XY model when n is equal to 2 and the Heisenberg model when n is equal to 3. And also it includes the self-avoiding walks. Finally, this plateau phenomenon should be observed in different probabilistic models. However, I think it had been taking less attention than it is worth. So I hope that people in the probability community gets interested in this question of plateau. I think it's a wonderful direction of research. That's all I wanted to mention. So thank you for paying attention.
Great. Thanks, Jiwoon. I don't know if you can see the applause.
Thank you.
That was great. I think we have a couple of minutes, so if there's any questions, now's the time. Sam?
Yeah, thanks. Thanks, Jiwoon. That was very nice. Hold on a second. Okay, cool. Yeah, so I just had a small question about your main results.
Yes.
It was a couple of slides in the end where you were talking about the non-Gaussian scaling limits.
Yes.
Yeah, exactly. So you have this condition that G needs to be small.
Yes.
So I had two. One is what is there an intuition for why that would be, and secondly, I was kind of curious as to. I thought maybe there would be a G on the right-hand side somewhere, but maybe.
Here,
Yeah.
you mean?
Yeah. I didn't see where it would disappear to, but perhaps, yeah. Maybe you can explain a bit more about that.
Oh,
Does it get
yeah, actually,
rescaled
I
out
dropped the
somewhere,
scaling
or
factor here.
does it get rescaled somewhere? I couldn't see where it would get removed on the left-hand
Yeah,
side.
so I think I dropped the scaling factor on the left-hand side so that
Okay.
everything looks more simpler.
Right.
But there should be an extra scaling that depends on G and all the parameters that I didn't want to talk about.
Okay, fine. No, that makes sense. Yeah, I just couldn't see from what you had written where the G would go, but yeah, that makes sense. And why does G need to be small? Is that for that scaling
That's
factor?
So we needed to apply the renormalization group method. So our renormalization group method is basically considers the phi-4 model as a perturbation from the Gaussian free fields.
Okay.
And looks at the flow of these parameters, G and nu and so on, how they develop as we look into different scales and so on. So in order to analyze that dynamical system, we need the initial values to be small enough.
Okay, right, that makes sense. Okay, thanks very much.
Yeah, thank you.
Okay, great. Good question, Sam. Okay, I think that's dead on 3 o'clock, so let's wrap it up. I see some people have said thanks for the talk and left already, so just to say thanks, Jiwoon. This will be going on the YouTube channel, so I'll let you know when that's posted as well.
Thank you.
Yeah, thanks again.
Then, well, good afternoon.
Thank you.
Yeah.
It was a really nice talk. I really enjoyed it. So I don't work in this topic. I worked on gradient models.